We're going to do some applications of centripetal force. It's just objects moving in a circle, you know. So let's say we have a car with mass 2,200 kilograms. It's traveling at a constant speed around a curve with radius of curvature 75 meters. Coefficient of static friction between the tires and the road is 0.73. And I want to know what is the maximum speed the car can travel at without sliding off the road. Right? So once you get past a certain speed, the amount of centripetal force required to keep the car on the curve will be more than can be supplied by friction, and then the car would go kind of skidding off into oblivion. So if you've got your road, got your car, and the tendency of the car is to move in a straight line, friction is supplying a centripetal force that enables the car to move around in a circle. If I say the radius of curvature of the road is 75 meters, that means this is part of a circle, and that radius is 75 meters there. Yeah. Now we know that the maximum static friction is mu times normal force. The value of the static friction can be less than that, but since I say what is the maximum speed the car can travel at, that means if the speed is any higher, there wouldn't be enough friction. So that phrasing means that we can plug in the maximum value of static friction into our equation. And we know that the net force pointing toward the center of the circle is the centripetal force, which is equal to mv squared over r. In this case, that centripetal force is being supplied entirely by that static friction between the tires and the road. And so this is our equation. And from that, we can solve. We want to find speed. So if we, and in the vertical direction, there's only normal force and gravity acting. So in the y direction, we have a net force of 0, and we have normal force going up, mg going down, so our normal force is equal to mg. So we got mv squared over r equals mu mg, masses cancel out, and by rearranging we get v equals square root of mu g r. And then we can plug in our values, 0.73 times 9.8 times 75, and get a velocity that's about 23 meters per second, 23.16, and so forth. Right? So if we've got a car going around a curve, that's kind of how things play out. You're just saying what the centripetal force is. This is the net force pointing toward the center of the circle, and plugging in the forces that contribute to that net force. In this case, there's only one. Another fun example involving centripetal force is sort of the same scenario, but now we have a banked curve. And we've still got this car going around the curve, but now if you take looking from the back of the car, we're on an incline, and then, the tires are in contact with the road, and the car is like, it's a beautiful drawing, I know. So you're going around the curve, but the curve is angled. And this, because that curve is angled, and now gravity supplies a bit of, gravity would give the car a tendency to slide toward the center of the circle, which enables you to go faster on the curve and still stay on the road. So a car with mass 1,700 kilograms is traveling around a bank curve with radius of curvature 61 meters. The car could go at 21 meters per second without sliding if no friction was present. The question is, what is the angle at which the road is banked? So in this case, we're not dealing with friction. If you do include friction in a banked curve, things get more complicated. Friction always makes things more complicated. But for now, we have no friction. We've got our banked curve. We've got our car, tires, car, on the curve. And we want to know what this angle is. Well, what forces we have acting? We have gravity and normal. And the centripetal force is the net force, but the center of the circular path is this way, in the horizontal direction. So because we have the net forces in the horizontal direction, and then we have a vertical force, it's actually more convenient to not rotate your coordinate system in this case. We do a little bit of similar triangles. We know that this is theta from before, which means that this is theta. So in the vertical direction, we have zero net force because we want the car to not slide up or down the slope. So, and that is, we have the normal force, the component of the normal force, which is adjacent to the angle, so that's normal force cosine theta going upward. And then we have gravitational force going downward, which tells us that the normal force is equal to mg over cosine theta. And then in the horizontal direction, some of the forces in the x direction, that's the total force acting in the x direction, in this case, is the centripetal force, which of course is mv squared over r, and all that's acting in that direction is the other component of the normal force sine theta. But then, of course, normal force is mg over cos theta times sine theta. So we have mv squared over r. Sine theta over cosine theta is just tangent theta. Masses cancel out. And rearranging, you can see that theta is the arctangent of v squared over gr. And if we plug in values, arctangent of 21 squared over 9.8 times 61. And punching that into the calculator gets that our theta is about 36.4 degrees. So that's the angle the car could go around the curve. Oh, sorry. That's the angle the car could go around the curve at without sliding up or down. So we just plug in y direction, x direction, and then we make our substitution of this in for the normal force. Mg over cosine theta, sine over cosine becomes tangent, cancel out an m and rearrange, and we can find that angle. I'm not going to go through this, but if friction is present, things become more complicated because first you need to figure out whether you can't add friction into your equations right away because you don't necessarily know whether friction is going to be acting in this direction or in this direction. You have to look at the rest of your forces and compare the velocity and the angle, and if the angle is bigger than this arctan of v squared over gr, if the angle is larger than that, then the car is going to tend to slide toward the middle and the friction would go up the ramp. If the angle is smaller than that, then the car would tend to skid off to the side and friction would be pointing in this direction. That gets kind of complicated because you don't know whether to add or subtract it until you've done that little comparison. One other application of centripetal force has to do with a carnival ride. Excuse me. A carnival ride that is called the Cajun Cliffhanger, or rather, well, it's called. I've seen it in different places. Where at the amusement park that I went to growing up, Six Flags near Chicago, it was called the Cajun Cliffhanger. And so what this ride is, if you look down at it from a top view, it's a circle. It's like a cylindrical shaped room. I'll use my slinky. It's like a slinky shaped room, and you go down inside of this room, and then this thing starts spinning faster and faster and faster. Okay, and so this ride is spinning around, and as it spins around, your tendency is to go flying off in a straight line, right? But the wall pushes you inward and keeps you on that circular path. And so then, in this case, the centripetal force is being supplied by that normal force from the wall, pushing you inward. So as that speed increases, then the centripetal force of course, increases because it's mv squared over r, which means that normal force increases. Okay. Now, if we think of a side view, you're sitting against a patch of wall, and as this normal force gets bigger and bigger, there's gravitational force acting on you going downward. As the normal force gets bigger, you have friction. And we know that friction, or the maximum value of friction, of static friction, is mu sub s times normal force. So as that normal force increases, the maximum value of static friction also increases. And at a certain point, when you get going fast enough, that static friction, the maximum value of static friction, when that maximum value is bigger than your mg, or equal to your mg, then you don't actually need the floor to support you. Friction from the wall will support you. And at that point, in the ride, what happens is that the floor drops down, and then you're just pressed up against the wall, spinning around and around. It's a lot of fun. And the video, there's a video right below this one, I believe, on RenWeb that shows that. And it's pretty cool. If you ever get a chance to go on one of these rides, do so. If you're not quite sure what I'm talking about, pause right now and take a look at the other video that I have put on RenWeb. It's an option. You don't need to watch the video, but it's fun. Anyway, so the condition for you being able to stay up is that mu times normal force is equal to mg. The static friction and mg cancel out. And this normal force is equal to the centripetal force, which is mv squared over r. So if you plug that in, you got mu sub s times normal force times v squared over r equals mg. Of course, the masses cancel out. And this is the relationship between all the variables involved. This is the minimum for the minimum velocity or minimum value of static friction that will allow you to float. The condition for you being able to be pressed up against the wall and for the floor to drop out and you to not fall. So that's a pretty cool application of physics in a carnival ride.